My name's Fiona, and I will be taking you through the story of how our current understanding of gravity really came to be, and a little bit about how gravity affects our solar system and the universe around us. So I'll start off by introducing myself. I'm a PhD student here at the Australian National University in Canberra. So what this means is that rather than just going to classes every day, what I'm doing most of my time is doing research. So I'm working on a research project, but I'm not doing it alone. So I don't have to come up with everything totally in isolation. I work with my supervisors. They'll give me ideas, they'll give me tasks to complete, and we'll hopefully come up with some kind of cool research all together over the course of the next 3.5 years. So before I came here, I was actually studying maths and physics at the University of Auckland. So I have a Bachelor of Science degree in maths and physics. And in high school, I studied physics, maths, chemistry, and I also studied history and music. And there's a bit of a history component here today in this story of gravity. So my research today, I now study supernovae. So these are the explosions which mark the deaths of stars, and I'm very interested in the deaths of stars which are around the same mass of us as our sun. So these are called thermonuclear supernovae, and they occur when two stars which are very, very low mass, they'll interact towards the very end of their lives and they produce a massive explosion. And I'm very interested as well in the subatomic particles which are produced by these supernovae. So they produce lots and lots of antimatter, and that's something else that I'm studying. So this photograph, this is a picture of the telescope here at Mount Stromlo, and the purpose of this telescope is actually to track space debris which is in orbit around Earth. So there we go, a little bit of a gravity connection here at Mount Stromlo. So let's have a think about gravity. So just think for a few seconds, what's the first thing you think of when you actually see the word gravity? So I'll give you a couple of minutes to think, and then we'll see if you think of some of the same things that I thought of and which I looked up and found images of. So what do you think of? Do you think of some kind of complicated mathematical, physical diagram and some working out there? What about a person who is associated with gravity? So this guy here is quite often associated with the word gravity. Do you think of things in space which are held together by gravity? So this is a big star cluster, it's a globular cluster, and all of those stars are attracted to one another by the force of gravity. Or do you think of something like the apparent absence of gravity? So astronauts, for example, appear weightless when they're in space, say in the International Space Station. Or what about words we associate with gravity? So things like black holes, or maybe relativity. Or if you've been watching the news recently, maybe even gravitational waves. So these are all things which I kind of thought of when I see the word gravity. Maybe you thought of something different. You can tell me at the end if you thought of something very, very different than I had here. So to start our journey in learning about gravity and how it affects the universe around us, I'm going to take us all the way back to the early 1600s, and I'm going to take you back to this guy here. So does anyone recognize him? If you recognize him, stick your hand up. Anyone recognize him? You recognize him? Yeah, so this guy is Johannes Kepler, and he was a German scientist. And Kepler was very much like the young scientists today. So he didn't just come up with his theories about gravity in a vacuum. He actually used his supervisor's observations, and he derived 3 very famous laws which describe the motion of the planets around the sun. So Kepler's supervisor was called Tycho Brahe, and Tycho Brahe has become very famous because at one point he was at dinner with a group of other mathematicians, and he got into a disagreement over a mathematical formula. And in order to settle this disagreement, Tycho and the man that he disagreed with agreed to a duel. And in this duel, Tycho unfortunately lost his nose. Now, I'm saying Kepler's a lot like students today. He worked with a supervisor. I've not yet had to save my supervisor from a sword duel, but, you know, the time may come, we'll see. So, Kepler's laws are what we call empirical laws. They only describe the observations. They're a mathematical relationship describing how things work, but they don't adequately explain them, so they don't actually give you any information on their own about the underlying physics. So let's have a look at Kepler's laws, and we'll start with his first law, which is called the law of ellipses. So the law of ellipses describes the shape of a planet's orbit around another mass, usually a star like the sun. So an ellipse, it's simply a squashed down circle. So a circle has a single point in the middle, and then you draw around, and the radius from the center to the edge is always the same. Now, if you were to squash down the circle, you end up with two sort of center points that we call foci. And in the case of a planet orbiting around a star, the star, in our case the sun, is at one of these foci, and then the planet orbits around. So one thing you can do if you want to have a go at drawing ellipses and kind of understand this is take two thumbtacks, stick them into a hard surface, get a piece of string and a loop the string around the two thumbtacks and then around the pencil, and then you can draw an ellipse. And one of those thumbtacks will represent the sun. So there are two quantities we use to actually describe what an ellipse looks like. So this is the semi-major axis, which is this quantity A. And then we also have the eccentricity of the ellipse, which is a measure of how squashed it is. So an ellipse with eccentricity of 0 is actually a circle. An ellipse with eccentricity of 0.9 is very, very squashed down. So this here has a moderate eccentricity, but it's still quite a high eccentricity. So Kepler's law of ellipses tells us that the orbit of a planet around the sun is an ellipse, and that the sun will lie at one of the foci of the ellipse, so one of these 2 points here, which would be those thumbtacks if you drew the ellipse like I described. So, the orbit of a planet around the sun is an ellipse. Let's have a think about our solar system. So, I've just plotted this here earlier on. So this shows in blue, if you can see the blue curve, that's the orbit of the Earth around the sun, and the sun's at the very, very center of this circle. Now, there are three other circles or ellipses you can see drawn here. There's a pink one here, there's a red one, hopefully you can tell the difference between those colors, and then there's a kind of light blue one. Now, one of these other three curves represents the orbit of Mars around the sun. So Mars has a much more eccentric orbit than Earth's. The Earth's orbit is essentially circular. So, which do you think is the real orbit of Mars around the sun? Who thinks so? If you think it's the red one, can you put your hand up so that I can see? So if you think it's that red curve here that represents the orbit of Mars, stick your hand up. Anyone think it's the red one? Okay, does anyone think it's the pink one? So this pink orbit here, does anyone think that that represents the actual orbit of Mars? Okay, and then what about the light blue one? Anyone think it's the light blue one? Okay, we've got a few votes for the light blue. That one's a popular one. So, I said that the orbit of Mars was a lot more eccentric than the Earth's orbit. And it is. The eccentricity of Earth's orbit is pretty much 0. And the eccentricity of Mars's orbit is around 0.09. And the red curve here actually represents Mars's orbit. So in practice, the orbits of the planets around the sun, unless you're able to very precisely measure the position of the planets, are essentially circular. So that just shows how incredibly good Tycho Brahe's measurements were way back in the 1600s for Kepler to realize that planets don't orbit in circles around the sun, they actually orbit in ellipses. Okay, so the second of Kepler's laws is I always think this is the more complicated one. This is called the law of areas. So it's a bit weird. And what it says is that the orbit of a planet sweeps out equal areas in equal times. So what this means is that if you were to calculate the area here, and then you were to calculate an equal area here and here, you can calculate that. There's a simple relation between this, what we call the arc length, and the radius here and here. If you were to calculate that, it takes the same amount of time for the planet to go from here to here as it takes the planet to go from here to here and then here to here. So what this actually means in practice is that the velocity of a planet orbiting around a star like the Sun is changing constantly with time. So if that planet was orbiting in a perfect circle, it would always move at the same velocity. But orbiting in an ellipse, it will actually move a little faster when it's closer to the star as it does when it's further away. So this is an animation which shows that. So you can see when the planet's further away from the focus of the ellipse, where the star is, it's actually moving a little bit slower than it is when it's very, very close. It kind of whizzes around really quickly. And the more eccentric the ellipse is, the bigger this difference you'll see. So if it's a very eccentric elliptical orbit, the planet will move very, very slowly when it's far away and much, much quicker when it's close. And this is just a consequence of the conservation of angular momentum, so the momentum associated with orbital motion. So that's the underlying physical reason, although Kepler didn't realize this. Kepler ascribed some kind of mystic reason for all of these laws, a religious almost reason for these laws existing. And the final one of Kepler's laws is what we call the law of periods. And what this says is that if you take the square of the orbital period, so the time it takes for a planet to complete an orbit around the Sun, that is directly proportional to the cube of the semi-major axis. So remember, the semi-major axis is that distance from the center of the ellipse to the edge of the ellipse that I showed you earlier. And this is actually quite a cool law in an unusual way. And it leads us to what my former supervisor, when I talked a lot about this, and it leads you to what you call a cosmic coincidence. So bear with me here because there's going to be some equations, and I promised I wouldn't put equations in the slides, but I had to show you this really cool thing. Okay, so if we express this law of periods in the right units, we'll actually find that Newton's gravitational constant g is a multiple of pi. So this is Kepler's third law. You might have seen this in class already. You might not have done this unit in class yet. You might come to this. Anyway, so here you've got the square of the period, you've got the cube of the semi-major axis, and you've got a whole bunch of constants out the front. So you've got 4, you've got pi squared, Newton's gravitational constant, 6.67 by 10 to the minus 11, some kind of units I can't remember. You don't need to remember that. And then you've got the mass of the largest mass in the system of things which are orbiting. So in the case of Earth and the Sun, that will be the mass of the Sun. So if we were to express t in Earth years, so t is equal to 1, and a in astronomical units, or AU, so the Earth is defined as 1 astronomical unit away from the Sun, and if we define m as the mass of the Sun, what happens then? Well, we find that t squared is just equal to a cubed, because 1 squared is 1, so 1 Earth year squared is equal to 1 AU cubed, which is just 1. And that means that g is equal to 4 pi squared. Now, that is not true in the SI system of units, which you'll be most familiar with using in class. But this system of units here is quite a common system of units for astronomers to use. So this is our cosmic coincidence here. And I've been talking about Newton's gravitational constant. And that leads us to the mid to late 1600s, and this guy here, who's probably a little more familiar than Kepler. So this is Newton. He has really fabulous hair that I'm jealous of. So Newton actually used Kepler's third law to develop his universal law of gravitation. So Kepler came up with these empirical laws which describe the way something is, and then Newton came up with laws which describe why these things are this way. Okay, so this relationship is one of those really important ones which astronomers and scientists use every single day. I mean, I used this every single day during the 4th year of my degree because my degree was based on motion due to gravity. So this is probably a relationship you recognize in a situation you might recognize. So you have two masses. They each exert a gravitational force on one another, and the gravitational force can be calculated using this formula here. So what this tells us is that all masses experience a force of attraction between them. So there's a force of attraction between me and the Earth below me, and there's actually also a gravitational force of attraction between me and the blow-up Earth I have here on the table. And if you've got like a pen on the desk next to you, there is a force of attraction between you and the pen. And if you're sitting next to someone, there's a gravitational force of attraction pulling you two together. So why is it that I'm aware of the gravitational force of attraction between me and the Earth, but not me and the blow-up Earth? So why is that? Because there's a force there, but I'm not being pulled towards this like I am if I fell off my chair and fell to the real Earth. And the reason for that is that the Earth is just so big, so massive. There's so much mass there that we don't notice the very small attractive force between us and other small objects around us. So I'm not being pulled towards this miniature Earth because it has a miniature Earth mass. I can throw it up in the air. It's really, really light, so there's very little force there. And that brings us to what we often think of as the absence of gravity. So here's a question. Is there gravity in space? Put your hands up if you think there is gravity in space. Put your hand up if you think there isn't gravity in space. Everyone thinks there's gravity in space. Yeah? Okay, well, you'd be absolutely right. There is gravity in space, but if there's gravity in space, why is it that astronauts float? If astronauts are floating, there's no gravitational force pulling them back to Earth. So why is that? So no matter where you are in the universe, you can be anywhere in the universe, there will always be a gravitational force acting on you. If you have mass, and there are things in the universe that have mass, there's always going to be a force of gravity acting on you. So the reason why in space astronauts are floating is because they're actually in free fall around the Earth. So rather than just falling straight back towards the Earth, what's happening is they're orbiting around at a particular velocity, which allows them to, so if they start off up here, what they actually do is they fall around the Earth, and they continue to fall around the Earth. So they experience what we call microgravity. So the acceleration due to the free-falling motion cancels out that force of gravity, and they experience an environment in which there's nothing pulling them down to the floor. And this is really useful if we want to investigate how things like plants or the human body adapt to living in environments where there's very little gravity. Of course, we're adapted to living on Earth, where there's always a gravitational acceleration of around 10 meters per second. But our bodies will react differently if we're in almost gravity-free environments. So this is just some of the research which actually gets done on the International Space Station. So what's happening with gravity today, and how do astronomers and astrophysicists and physicists work with gravity today? So if you're learning Newton's laws, so F equals ma, Newton's universal law of gravitation, and Kepler's laws in school, you'll actually find that professional astronomers still use these laws today to study our universe. So I'm going to tell you a bit about a problem which I studied from the very first research papers that I ever wrote. So we'll start off with what we call the two-body problem. So if you have a single mass hanging out on its own, there's no other mass near it, by Newton's second law, F equals ma, there is no force acting on it, so it just hangs out on its own. But what happens if you have another mass exerting a gravitational force? So this mass exerts a gravitational force on this one. This mass exerts a gravitational force on this one. So if you look at Newton's second law, F equals ma, there must be some kind of acceleration force between them, therefore they're going to change their positions. So this leads us to what we call the two-body problem. And this animation shows it here. So the two-body problem it describes the motion of two masses which are only experiencing the force of gravity between them. So say you had two stars. They will actually orbit one another a little like the animation's showing. They'll orbit some common center of mass, and they'll orbit in elliptical orbits. Now, the cool thing about the two-body problem is I can write down an equation which precisely describes where that mass is going to be, either of those masses, at any time. So it's kind of like a solved problem. But what happens if not only these two masses are here, but I was to add a third mass, which I haven't got to blow up something else. So we're going to have to look at an animation for that. So you have to look carefully because this one isn't quite so obvious. So here we have three masses in a 3D box, and they're all interacting with one another through the force of gravity. Now, just watch them for a while. They're doing some pretty crazy stuff. So who reckons I'd be able to write down a formula which precisely describes the location of each of those masses at every point in time? Who thinks I could? You reckon I could? Who reckons that that is an impossible task and I'd be wasting my time trying to do it? I reckon it's an impossible task, but I've got a head start because I know that it's an impossible task. So this is what we call the three-body problem. And it's impossible to write down a mathematical formula that describes the motion of, I've called them particles, but they're masses. Often in astronomy, we refer to a mass, like a spherical mass, as a particle. It's just a simplification when we're doing simulations. And this is because the motion is chaotic. So a chaotic system, like this one, if I was to start off those three individual masses at just a tiny bit further apart, the patterns they trace out would be completely different. They would be nowhere near the same as what they've traced out in this simulation here. And the same is true for 4 or 5 or more particles. And this leads us to a pretty big problem when we want to study objects like these globular clusters. So a globular cluster is a collection of stars which have all formed roughly around the same time, and they're all bound together by one another's gravity. So globular clusters, this one's called 47 Tucanae. It's in our galaxy, it's just outside of our galaxy, and it contains, I think, it's either 1 million or 1 billion stars. Anyway, there's a hell of a lot of stars there. They're all roughly around the mass of our sun, maybe a little bit lighter, maybe a little bit heavier. And every star in that globular cluster exerts a gravitational force on every other star in the globular cluster. Now, one problem which scientists want to try and solve is to understand how these stars actually orbit around one another and how they interact, and even whether they can collide in the very center of these globular clusters. This is what we call the Nbody problem, and this is what I used to work on. And the Nbody problem is entirely based on Newton's law of gravitation and Newton's second law. So these are two laws of physics you probably are already well aware of, and we use them together with incredibly powerful supercomputers to try and understand how globular clusters form, how they can be broken up when they get stretched apart by the force of gravity exerted by a galaxy. So very, very simple mathematics, but a very complicated problem. And it's a really cool one, so that's one that I used to actually work on. And Kepler's first law actually led to an even more important discovery about our galaxy. This was less than 20 years ago. So this was discovered kind of shortly after I was born. So this image here, this animation, what's it showing? So all of these funny kind of sort of rainbowy points of light, what these are is these are stars which we actually observe in the very, very center of our galaxy. And these were observed by Andrea Ghez and her group at the University of California in Los Angeles using the Keck telescope, which is a big 10-meter telescope. So they pointed at the center of the galaxy, they find the positions of each of the individual stars in the center of the galaxy, and they track them over the course of 5 to 10 years. And what they found is these stars were tracing out these beautiful Keplerian elliptical orbits around nothing. So there's a fake star in the very center of this animation. That star, it doesn't exist. So all Gez's team saw were these stars tracing out these elliptical Keplerian orbits around absolutely nothing. So what were those stars orbiting? What's hiding in the center of our galaxy? Well, it turns out you can use Kepler's laws, which describe those stellar orbits, together with Newton's law of gravitation, to calculate the mass of the object the stars are orbiting. So each of those stars are around 15 times as heavy as our sun, so they're very, very big. But it turns out they're orbiting an invisible mass 4 million times as heavy as our sun. So something incredibly massive, which emits no visible light, which was detected by Gez's team. And what that thing actually is a supermassive black hole. So like the song by Muse, if you're a music fan like me, they really exist, and there is one at the very center of our galaxy, and it's 4 million times the mass of our sun. It doesn't emit any light that we can see using optical telescopes. Our telescopes aren't big enough to see any trace of optical light it's emitting. But what we can do is we can point big X-ray and gamma ray and radio telescopes towards the center of our galaxy. And if you look at X-ray images, so this is an X-ray image here of that same region that I was showing you in that animation. And there's some very bright light, bright X-ray light here in the very middle of this image. And what that is that's actually X-rays being emitted by the region around that 4 million solar mass black hole. So lots of particles and dust and debris gets accelerated in what we call an accretion disk around the black hole. And as it's accelerating, an accelerating charge, so these things have electrons and protons and all kinds of cool stuff in them, they're accelerating and they're emitting light, and they're emitting X-rays, they're emitting radio waves, and they're emitting gamma rays, which we detect. So that's how we discovered that there is almost certainly a supermassive black hole at the center of our galaxy. And that leads us on to this guy's work, and I'm going to finish up by telling you a little bit about Einstein and his predictions of general relativity, and how we've confirmed that Einstein's theory of general relativity is almost certainly an accurate description of gravity. So, Einstein predicted that a lot of things which we know today about gravity would be true using mathematics. So he predicted black holes, he predicted gravitational waves, which we'll get to in a minute, and he predicted sort of relativity, so this idea that space and time are this single fabric. And when Einstein's theories were first published, some scientists found them very hard to believe. So Einstein's description of gravity is a little different to Newton's, but it doesn't actually contradict Newton's ideas. You can recover all of Newton's laws from Einstein's mathematics. So this is how science works. As we learn more and more, we don't necessarily say that was wrong in the past. What we do is we add to this scientific knowledge as time goes on. So what did Einstein's gravity predict? Well, the first thing that Einstein predicted was that the position of Mercury can't just be predicted using Newton's laws. So Newton's laws predict that Mercury orbits the Sun in a slightly eccentric orbit, and it actually drifts around in what we call apsidal precession. So the ellipse that Mercury orbits in is just rotating around very, very slowly, much slower than this animation here. but nonetheless, this ellipse is rotating and rolling around. However, the observations of Mercury, they couldn't explain Mercury's orbit was precessing too fast. But when Einstein came along, he said, well, if space and time is curved around the sun, then Mercury's orbit should precess just that little bit faster. So he was actually able to explain these observations of Mercury's orbital precession. And he also predicted the existence of black holes. So a black hole is, if Earth makes like a curve, a bend in space-time due to its mass, like a bowling ball on a rubber sheet, a black hole is an infinitely deep well in this rubber sheet. So nothing can escape. It's like those charity coin things where you spin the charity coin down and it goes around and around and around and eventually falls in when it loses most of its velocity and most of its momentum. So he also predicted that these infinitely deep wells in space-time that we now call a black hole would exist. So we managed to prove that many aspects of Einstein's theory were correct, but there was one thing which remained completely unobserved until September 14th, 2015. And scientists thought we would never ever see this. So does anyone recognize this image? Has anyone seen this before? Okay, so what this is it's actually the sound produced by two black holes spiraling closer and closer and closer and closer, and then merging together. It makes a funny kind of noise. It's this, what we call a chirp, and it sounds kind of like whoop. It's a funny little noise. And we actually detected this gravitational wave signature back in September last year. So what's happening is the two deep wells in space and time are orbiting closer and closer to one another. And as they get closer, it's like ripples on a pond. They spread out across space and time, and eventually they reach us here on Earth. So if you could get really, really close to these two orbiting black holes, that bending of space and time would actually distort what you see behind the black hole. You'd see something like this image here. So I'm going to wrap up now so we still have time for questions. But there's still a lot we don't know about gravity and how it shapes our universe. There's lots of different theories now for how gravity works on very small scales with quantum mechanics. So there's a lot still to learn. And our understanding has changed vastly over the past 500 years, so all the way from Kepler all the way to Einstein. And it will continue to change into the future. And this is just a really good description of how science, it never stands still. It's constantly changing, and there's always going to be more things to learn about our universe. So I'd love to answer any questions you have. And thank you very much for listening.